Good afternoon, everyone. Today we're going to do a problem relating to z-scores. So in a population, we have 50% of adults being taller than 180 centimeters, and at the same time, 10% being all the way taller than 200 centimeters. And so we're tasked with finding the mean and the standard deviation of this normal distributed data set. So first off, if we have 50% of adults being taller than 180 centimeters, we know right away that our mean is 180 centimeters, right? Whenever we have a data set that is normally distributed, then we have this classic bell curve shape, and we know that our mean is always smack dab in the middle of our bell curve. And so that means that 50% of the data set lies above the mean, and likewise, 50% of our data set lies below the mean. And so if 50% of adults are taller than 180, then 50% are also shorter. And so our mean must be this 180 centimeters, okay? Now, if only 10% of adults are taller than 200 centimeters, then we know that that's gonna be somewhere around here, right? Where only 10% are further along in the height distribution, right? And so if only 10% and this is at 200, right? And so if 10% of adults are taller than 200, then that also means at the same time that 90% are short, right? And in relating this to our z-score table, this 90% is to the left of our data point of 200, right? So we can now use our z-score table, and we can look for a probability of 90%, right? So let's figure it out here. So we have a probability of 90% here, right? Because we always want the probability that is to the left of our data point, so 90% probability, whoops, it's not how you spell probability of 90%. Converting that to a decimal is, of course, 0.90. And so we're going to look at our z-score table, and we're going to look for the cell with the decimal value that's closest to 0.90, so as close as we can get. And if you go ahead and do that on your own, you'll find that the closest cell is 0.8997 for a z-score of 1.28. You might think it's 0.9015, but that's actually 1500ths away rather than 300ths away. So we'll use the 0.9987 at 1.28 of a z-score. So I'll say in brackets use 0.8997, and using our z-score table, we have a z-score of 1.28, okay? So that means that we already have our mean, right? Our mean is 180. Now, we have a z-score of 1.28 for the individual data point 200, right? Because for this data point, 9% of our data set was to the left of it, meaning it had a probability of roughly 0.90, which meant it has a z-score of 1.28. Now we can use that information along with our z-score formula, that z is equal to xi, meaning the individual data point that we're going to use, minus our mean divided by our standard deviation, right? And now we have z, we have the individual data points that we're going to use. I'll call that our xi in this case, and we have our mean, and so we can now solve for that standard deviation, because that's the only unknown that's left in this equation once we fill in our values. And so let's go ahead and do that. Z is going to be 1.28, right? Just filling in this value in for Z. Xi is going to be 200 minus mu, that's our mu, is going to be 180, divided by our standard deviation, and that's what we're going to solve for. So this is just algebra. We're going to have 1.28 is equal to 200 minus 180, that's a difference of 20. So 20 divided by our standard deviation, right? You've probably seen equations like this before. Our unknown is in our denominator. We want to get rid of that. And so let's multiply by sigma to cancel out the sigma in the denominator. We always multiply both sides by the same thing. And so 1.28 times sigma is now equal to 20. And of course, you know how to finish this off. Divide both sides by 1.28 to cancel that out. Divide by 1.28, and we get a value for sigma of 20 divided by 1.28, which will be around 14 or 15. If I were to guess, 20 divided by 1.28, 15.6 to one decimal place. And so our standard deviation, sigma, is 15.6. And there we go. Right? There's an easy way to kind of verify if that is at least reasonable. If our standard deviation is 15.6, then with the mean of 180 and our data point at 200, 200 is 20 points above the mean. 20 is a bit more than 15.6, so does it make sense that it has a z-score of 1.28? Well, a z-score, let's figure what that means. That means that 200 is 1.28 standard deviations above the mean, right? So 200 is 20 centimeters away from the mean. Does it make sense that 20 divided by the standard deviation is roughly that many standard deviations above the mean? That certainly makes sense, right? 20 divided by 15.6 is probably exactly 1.28, and so that should at least give you some confidence that your answer is reasonable. So, I hope this helps, and thanks for watching.